Okay, so today we will be changing the subject. So if you remember up to now we have been only discussing linear motion and trying to describe and analyze how linear motion takes place, what are the principles governing linear motion. Now today we will be starting rotational. So before we go on with rotations, do you have any questions to ask? Questions? Any questions about the linear motion, momentum, energy, potential energy? Now, because, yes? No. Other questions? Things that you don't understand about the material rather than solving questions? Now, because when we are discussing rotations, now we will closely follow what we had done in the linear motion case. So if you remember what we have done in the linear motion case, we were first discussing kinematics. We had if you remember in kinematics, what we discussed was displacement. Now we will be describing angular displacement. Then we had the velocity. Now we will have angular velocity. Acceleration in the case of the linear motion. Now we have angular acceleration. Now they will closely follow one another. And when we write down the equations describing these properties, we will see that the equations also are closely related. Now we have the kinetic energy, which will be the more or less we have the rotation, the kinetic energy corresponding to rotation. We have momentum. Now we will have angular momentum. Before we had the linear momentum describing the translational motion. And we had the dynamics. Linear dynamics, if you remember, it was the Newton's laws that described how the motion changes. Now we will have the angular dynamics, if you like. Now in the linear motion case, we had the mass. The analog of mass in this case will be the moment of inertia. We will see that the concept is quite similar. The role of mass in one-dimensional case would correspond to what we call the moment of inertia in the rotational case. And everything will have more or less have this parallel between one and the other one. We had the conservation of momentum. Now we will have the conservation of angular momentum, etc. Now, first, let's try to describe what the motion. But before that, we will not be dealing with general rotations. We will be dealing with only some simple cases of rotations. Now, the simplifications we will assume is that we will have rigid objects. We will study rigid body motion, which basically means that the object doesn't change its shape. Like this wheel. Now, of course, this kind of rubber, the rim, so it changes its shape slightly. We will just ignore the effects of such changes. So this is the wheel of my bike, nothing fancy. And we will be studying only with rotations around the fixed axis. In which it will be, most of the time, the axis is fixed, or at least orientation is constant. Let's say almost constant. So for example, we will study motion like this when you're riding your bike. Yeah, this is the axis of rotation. The wheel is rotating around this axis. It will be always pointing in the same direction. Of course, we can have translational motion of that axis that we will also study. But we will not study this motion. For example, if you try to rotate it like this we will not study. Now there is this gyroscope example. So for example, if you just take this wheel from one side only, no rotation, it just falls down. If you set it spinning, not even a reasonable angular velocity, it will not fall down. This is in fact why the bicycles are quite stable. Although they go on two wheels, they are quite stable. And if you have some speed on the bike, it's almost impossible for you to fall down. Now, in this motion, of course, the rotation axis is constantly changing, but that change is so small that it can be neglected compared to its rotations around this axis. So this we will study eventually. So these will be the materials we will be covering. Now let's start with the first one, the kinematics. How do we describe rotational motion to start with? Now basically what we would like to do is, up to now we have been always dealing with objects that were either point-like or their orientation didn't change. Now we will be looking at objects whose orientations change. So we would like to know a way of specifying the orientation of the wheel. Now, just like in the case of the one-dimensional motion, if you remember the translational motion, when we wanted to specify the position of an object, what we did was we just chose some reference point. In this case, let's say this is the motion we will study, this rotation. Now, we should choose first a reference axis, reference orientation. Let's say this is my reference orientation. Now, I can describe how much it rotates, or I can specify the orientation of this wheel by specifying how much it rotates from this reference orientation. So if I rotate it like this, let's say now it has rotated like 90 degrees. Its angular displacement, angular rotation is 90 degrees. Now to determine this 90 degrees, what we usually do is we just take some point on this object, just take one line on this object. So here is our object. It is rotating around this axis. This is our rotation axis. Let's say just choose some point, P, and consider the line connecting our reference point to that point, P. This is just a hypothetical line that we imagine. Now, in the case of this wheel, I can just take this thing over here so that I can easily identify it. Now, when it rotates, what will happen is it will just its orientation will be, this is the rotation axis, it will be something like this. And the point P is now over here. This is my point P. Before it was in this orientation, now it's in this was its initial orientation, initial line. This is the final line after it has rotated. So we can talk about this angle, delta theta. Now we can choose this axis if you like. This is the orientation of my object. If I know this theta, then I know the orientation of my object relative to this reference axis, reference direction. And if I measure the angle between these two orientations, that gives me the angular displacement. This delta theta is the angular displacement. Now, just like in the one-dimensional case, we can also say this angular, if you rotate in one direction, we can say that it's a positive rotation. If it rotates in the other direction, we can say it's a negative rotation. So if, let's say, this is the positive sense of rotation, now it's this angular displacement, it's, let's say, positive 90 degrees. Now its angular displacement is negative 90 degrees. So this angular displacement can also be positive and negative, depending on your choice of which sense is positive or negative. Now, once we have this angular displacement, the remaining definition, like the angular velocity, the angular acceleration, just follow the one-dimensional analog. So we will define the average angular velocity to be our displacement divided by delta t. This is average angular velocity. Now the instantaneous one, you just take the limit as delta t goes to 0. Now you can talk about the change in the angular velocity. Now since delta theta can be both positive or negative, this delta theta, the angular velocity can also be both positive or negative. If you take this example again, rotation in this sense, let's say in the counterclockwise sense is positive rotation. Rotation in the clockwise sense, let's call them negative rotations. So now this object has a negative angular velocity, no, positive angular velocity. Now if it is rotating the other way around, now it has a negative angular velocity. So the angular velocity, just like the one-dimensional velocity, can be both positive and negative. And so we can also define the angular acceleration, the average angular acceleration, delta w by delta t, and we can define the instantaneous one as the limit delta t goes to 0. These are just analogous to the ones we had in one dimension. In fact, mathematically speaking, they are the same equations, the same definitions. Now, if you look at this one, now it has 0 angular velocity, now it has a positive angular velocity. We say that this has undergone a positive acceleration. Now it has 0 angular velocity, now a negative angular velocity, so the change in the angular velocity is negative. So we can say that it had a negative angular acceleration, at least for some time. Now the angular velocity is constant, so there's no angular acceleration. Now, any questions here? Let's just make a table of comparison about the similar quantities. The one-dimensional case, we had the angular case. Now in the one-dimensional case, we have the displacement. We usually denoted it by delta x. Now we have this delta theta. Now in the one-dimensional case, we had the average velocity. This was delta x over delta t. Now we have the average angular velocity, delta theta by delta t. And we have the corresponding instantaneous expressions. Once we know the velocities, we can talk about the change in the velocity and the average acceleration, which was delta v by delta t. And the angular acceleration, the average one, delta w by delta t. That's it. Now this is, of course, once you know the displacement, its position as a function of time or its orientation as a function of time, you can just calculate the other angular velocity and the angular acceleration. But you can also go the other way around. So if assuming we know the acceleration as a function of t, now in this case if we know the angular acceleration, now we can talk about the change in the velocity. So the velocity at the time t would be nothing but v0, the velocity at a given time t0, plus all the changes in the velocity from the time t0 up to time t. A of t prime dt prime. Well, we have the analogous in the angular moment. In the angular case, we have the analog of the velocity was the angular velocity. Angular velocity at time t is the angular velocity at time t0 plus the change in the angular velocity. We just sum all the changes, that is alpha of t prime dt prime, from the initial time to the final time. And one more step, we can calculate the position as a function of time. Or before we go to the position as a function of time, in the case of constant acceleration, v of t was equal to v0 plus a0, t minus t0. In the rotation case, it is angular velocity at time t is equal to the initial angular velocity plus alpha 0, t minus t0. And for the, once we know the velocity as a function of time, you can calculate the position as a function of time. X of t is equal to x of x0 plus the changes in the position, v of t prime dt prime, from the time t0 up to time t. Well, in the case of the angular variables, we have the angle or the orientation, theta 0 plus from t0 up to t, omega of t prime dt prime. Or again, back in the special case of the constant acceleration, x of t is equal to x0 plus v0 of t minus t0 plus 1 over 2 a t minus t0 squared. And in the case of the angular variables, we have theta of t is equal to theta 0 plus omega 0 t minus t0 plus 1 over 2 alpha t minus t0 squared. So the expressions up to this point is at least analogous, and this will continue all the way. The expression, the mathematical expression we have in the one-dimensional case will be almost identical to the mathematical expressions we have in the rotation case. Of course, you have to make the analogous replacements. Like the position is now the angle, the position is now the angle, the linear velocity is the angular velocity, the linear acceleration is the angular acceleration. Of course, what they imply, although mathematically they're identical, what they mean for our physical system will be completely different. In the case of the one dimension, we are talking about this translational motion, but in this case, we are talking about this rotations. Now, any questions up to this point? Now, although we will be dealing with rigid bodies most of the time, now in general, you can talk about the angular velocity in general. Now, let's do an example. Now, whenever we are talking about angular quantities, like for example, in this case, we are talking about rotations around this axis. It's important to specify which axis you are talking about, or your reference points. Now, suppose you have, you chose some coordinate axis, and your friend is just stands over here. He just walks on a straight line. So does he have an angular velocity relative to your reference point? This will be kind of one of the counterintuitive examples. Just take your reference point as yourself. You are your reference point, and I'm walking straight, just like this. Do I have an angular velocity relative to you? Yes or no? Yes. How many of you think it is yes? How many of you think it is no? The others? I'm just walking like this. I'm not doing this motion. I'm just walking straight. Why do you think I have a linear angular velocity?
mesafeyi R kabul edersek hocam, siz tam bir noktadan benim etrafındaki çemberi, R yarıçaplı çemberi bir noktadan T'ye geçmiş oluyorsunuz hocam. O noktada da sadece o noktada angular velocity.
Well, let's see, I'm walking like this. Now the circle is like this, right? And I'm definitely not tangent to it. I'm not tangent to any circle. But you see, when you determine whether something is rotating or not, if you remember our definition of the rotation angle, this is how we define it. The rotation is defined as the rotation of this line. So as I'm walking in a straight line, to watch me, do you rotate your head? It is this line. Your head is following this line. So if your head is rotating, that means theta is changing. If theta is changing in time, then there's an angular velocity. That is the definition. Of course, I'm walking in a straight line, but nevertheless, relative to you, I have an angular velocity. Okay?
But your linear velocity and the angular velocity are the same, right?
Well, let's see. Can the angular velocity and linear velocity be the same? Let's look at them. Now, how do we define the angular velocity? This is the definition of the angular velocity. Delta theta by delta t. This is the definition of linear velocity. Delta x by delta t. Now, what is the unit of angular velocity? The unit of angular velocity is radians per second, which is in fact 1 over second. Or, well, they are all 1 over second. The unit of linear velocity, meters per second. They can never be equal. They are completely different quantities. But it's a valid question, how are they related? If you take a rigid body, let's say, this is the axis of rotation. We have a rigid body. This is at t equal to, let's say, t0. And then we have the same rigid body after some time. It will look something like this. Now we can choose some reference point to specify how much it rotated. So let's say this was the initial line. Now that point is somewhere over here. This is the, after some time, t is equal to t0 plus delta t. This is delta theta. Or if you look at here, the wheel is rotating. If you just consider an arbitrary point, let's say this point, as it is rotating, that point has an angular velocity relative to the rotation axis. But at the same time, at any given instant, it has a linear velocity. So they are both related. If it is at rest, angular velocity is 0, linear velocity is 0. If it is rotating, there is an angular velocity, there is a linear velocity. Now, how we can relate them? Now, you see, since it's a rigid object, its shape doesn't change. If its shape doesn't change, this distance is always the same. So as the object is rotating, this point over here is basically doing some circular motion. It's going around a circle. Well, we had already studied circular motion. This is not necessarily a uniform circular motion, but nevertheless a circular motion. It will be carrying out circular motion. Now, what is the distance it covered? Let's say this is the distance r. I'm not asking for its displacement, but between these two times, what is the distance it covered? How can we calculate the distance it covered? Radius times delta theta. So this distance over here, let's say L, or delta L is r times delta theta. So is this clear? Do you remember this? since we are measuring all the angles in terms of radians, in fact, this is the definition of the radian unit. If I divide both sides by delta t, still I have the same equality. But you see, delta L over delta t is nothing but the speed of my object. Let's say v. It's not the velocity vector, it's the speed. V is equal to r times omega. So again, if you go back to this example, my wheel is rotating. This point has some speed. This point will also have some speed. But since this point is further away than this point, they all have the same angular velocity. They are on the same rigid body, so the angular velocity is the same for all the points. But the linear velocity of the point that is further away from the axis is larger because of this dependence on the distance from the rotation axis. This r over here is the distance from the rotation axis. And if I take this one, my rotation axis is fixed. So this point is rotating faster than the point over here. And in fact, the origin, where r is equal to 0, it doesn't have any linear velocity. Again, do you agree with this? Any questions on this one? Yes. Okay. Okay, so let's see. Your friend has this nice comment. Let's check the units. You should always check your units. V equals to r times omega. Unit of V should be equal to unit of r times unit of omega. So what is the unit of the linear velocity, linear speed? Meters per second. R, meters. Omega, radians per second. But this is equal to meters per second, since the unit of radian is in fact 1. You see there, if you look at this definition of the radian, you see radian, delta theta, is defined as delta L over R. So delta theta, the angle doesn't really have a unit. We put some radian over there just to emphasize that we are talking about an angle, but it is not really a unit. So that's why, although if you just look at this equality sign, it doesn't seem to be correct, but this radian over here is, in a sense, it's like just like a placeholder. It holds a place over there, but it's just one. So the units are consistent.
If we expect our angular velocity like speed of light, what will happen?
Okay, so let's start with your comment. If the angular velocity is equal to the speed of light, okay, that's what was your comment, right? Can the angular velocity be equal to the speed of light?
Yes.
No.
Units.
Why not?
O zaman lineer velocity speed of light fazla oluyor.
Linear units do not match. The angular velocity cannot be equal to the speed of light, because speed of light has units meters per second, angular velocity has units 1 over second. They can never be.
The black hole near the light passing, the black hole, and we are expecting or we are assuming the light is bending
Okay.
and passing like a curve, so it could be angular.
Angular velocity can be large, but you cannot compare angular velocity with speed of light. Never. You cannot compare, it's just like comparing apples and oranges. They cannot be equal. They are completely different objects. But of course, you are justified to asking, what if the angular velocity is so large that is it possible that the endpoint moves at the speed of light? No, that's not possible. I mean, when the objects start moving quite very fast, the concept of a rigid body doesn't make any sense. So that was one of our initial simplifications. We will be only treating rigid objects.
What if, according to what he said, we take the limit of the radius as it goes to 0?
If the radius goes to 0, I mean, I can take the radius go to 0. This point has a radius equal to 0 and it's not moving.
It's just so fast, but it's just.
Now, the angular velocity is constant. For this rigid body, angular velocity of all the points is the same. So, this point is again, angular velocity is 0, the same. The linear velocity is 0, it's not moving. If I do the same thing here, it has a linear velocity. But if it is so big, then, okay, as you go further away, you see this R is increasing. So if you would just blindly apply this result, there is a value of R at which the speed eventually becomes the speed of light. But I mean, we will not be dealing with such systems. For such large systems, it will break down. It won't stay a rigid object anyway. But reaching the speed of light is not that difficult. In the sense that just rotate around yourself, for example. The sun was moving faster than the speed of light relative to you. That's not a problem.
In your straight line motion, your distance from our reference plane was changing.
True.
But you said that we can treat this as a rotational motion.
Well, you see, my motion like this. In a sense, you can say, put it in this way. What we have done up to now was we just chose x, y, and z axis to describe motion. I can as well, if you want to describe my motion, you don't have to just choose x and the y axis. You can say that, okay, you will tell me what is our radial distance and what is my angular orientation relative to you. So those two information is also enough to describe my motion.
So it's not necessary to have same distance from the rotation.
No.
Rotation
No.
axis.
This is not a rigid body.
So it's not a part of the definition.
Which one? The angular velocity. True.
The distance from the
No.
rotational axis.
The distance doesn't matter. No. It's the only thing that determines the angular velocity is if you just point to your object, how fast does your arm move? That is the only thing relevant in defining the angular velocity.
When you moved here from there, did you have angular acceleration?
Well, let's see. Point your hand. I will be moving somewhat fast. I'm moving at constant velocity. So what do you feel? Did your hand move faster when you are here or no? Or just imagine like this. I'm moving along a line. Eventually I will go to infinite distance. How will you show my position? Okay, so eventually I will go over there, right? But from here to here, my angular velocity is almost 0, right? I mean, I reached that point in, let's say, 2 seconds. Now, from that point onwards, I will take infinite amount of time. So my angular displacement from here to there is very small, although it took infinite amount of time. So I should be slowing down. But I moved from there to there also in 2 seconds. So the angular acceleration cannot be the same. I'm quite fast over here, right? But from here to there, I'm very slow. There's angular acceleration. Other question? If you have any doubts, you should ask now. Now, since everything is so similar to the linear motion case, I will just move forward quite fast. I will not be spending as much time as we did in the one-dimensional case. This example, okay. Your friend was asking me, okay, as I'm moving along this straight line, I have some linear angular velocity. So you agree, all of you? Your friend was asking me, do I have an angular acceleration? So to determine my angular acceleration, I have to see if I have any change in my angular velocity. Now, let's just imagine I was over there to start with, and I went along a straight line until infinity. This is my initial point, initial orientation. I would move that distance from there to the other end of the room in, let's say, 5 seconds. Okay, so my angular displacement is something like 160 degrees, let's say 150 in 5 seconds. So it's 30 degrees per second. That is my angular velocity, average angular velocity as I go from here to there. Then from that point on, I go until infinity. But when I go to infinity, this will be my orientation eventually. I go from this angle to this angle in infinite amount of time. So my average angular velocity after that point until I reach infinity is almost zero. So I have 30 degrees per second average velocity, angular velocity as I moved from that point to that point. And as I moved from that point up to infinity, I had some zero angular velocity. So my angular velocity definitely changed. I should have had some angular acceleration, and which hopefully you will calculate in the homework.
Can't we do the straight line motion? Can we still use the relation between the angular velocity and the wave?
No, this relation will still be valid. Of course, there is one problem here, though. This will be the tangential linear velocity. Now, because you see, now yes, this will be always the tangential linear velocity. For example, in this example, I could at this point, just take this point, not a rigid body, but this point could have started from here, went with the same angular velocity up to this point, let's say. Then definitely its speed will be larger than r times omega, because it will also have some radial speed, not just angular speed. This is the tangential velocity. And once we have the tangential velocity, we can also talk about the angular tangential acceleration. Assuming we are only looking at the rigid body, r times alpha. Now, if you are looking at a rigid body, any point on the rigid body will have a linear speed equal to r times omega. And it will have this tangential speed, r times alpha. Will it have a centripetal acceleration? If, let's say, suppose we have an object, this one, the rigid object. There is no, so it is rotating with some constant angular velocity. There is no angular acceleration. So, and you pick one point. Does it have an acceleration? Well, this expression tells me that it has zero, no? Yes? Yes? This one.
Yeah. Now, we know that with linear velocities, I can see the rate of change of displacement.
Okay.
And with that, I have the unit for displacement. Now, I have a problem with the fact that you said you can omit the bar, because if you omit the bar, then
We can omit which one?
I mean, you said when the v over r gives you, because that's eventually you have something value over 1 second. That's what you have eventually.
Okay.
Value over 1 second. And then if you equate the value over 1 second, you know the unit of the value over that 1 second equals
Here.
Good. Yeah, that is. I think you move to
Not this one.
Yes.
This one. Here, radians per second, okay?
Yeah, I saw 1 second. 1 over.
Now, radians is just one. It's not really a unit.
Radian is not unit.
No.
Then I don't know why we should define. I don't know what we define angular velocity by. If radian is not the unit, then
Now,
I don't know.
the actual unit of angular velocity is 1 over second.
So why do we call it angular velocity? I mean, I know
Because
angular velocity is a rate. That's angular velocity is a rate. So why do we call it angular velocity? If it's not, in that case, it's just a value over time. So I don't know.
now, you see, the angle doesn't have a unit. And the rate of change of the angle is what we call the angular velocity.
That's the problem I have because I'm comparing the velocity that is attached to the angle. Maybe we should call it something because if we say angular velocity, I have to look at the rate of change of a particular value.
Yes.
So I said, in that case, I have to look at the rate of change of something.
Okay, the
If
angle.
something doesn't have the definition, then
No, I mean, I'm not saying the angle doesn't have a definition. The angle doesn't have a unit. You see, if you are measuring distances, if you tell me 5, it doesn't make any sense. If we are talking about angles, and we agreed that we will be talking about the angles in radians, you tell me an angle is 5, that makes perfect sense. The angle will be just 5.
the angle is 5.
That's fine. 5 would be more or less, in terms of degrees, 5 would correspond to something like, I don't know, 220 degrees or so, more or less. So that's why angle doesn't have a unit in our definition of the way we define the angles.
Angle, but if I define it another way, angle has a unit.
No, angle, look, in our definitions, in our framework, angles do not have any units. But to emphasize that a given quantity is an angle, we put this radians, which is just 1.
So what is the definition of degrees? Why do we use degrees in the first place?
We don't use it.
We don't use
I will not use it. I will use radians all the time. I mean, once you get used to it, I will always use the radians, never degrees. Other questions?
If the velocity is not tangential, can we say the velocity is equal to average radius times average angle?
If you want to say that, you have to tell me what do you mean by average radius. Now, of course, you can always write the velocity as some quantity multiplied by some other quantity, but I mean, it doesn't really make sense.
When you motion like this,
Okay.
the radius is changing.
Okay.
The average radius and the average of the angle using.
Okay. Well, the radius eventually goes to infinity if I keep moving until infinity, so the average will be infinite. So it doesn't really make too much sense.
But if we take two specific points,
So you mean between that point to this point? Well, of course you can come up with a definition. But the problem is, will that definition be useful in a given circumstances? So, or if it will be useful, everybody will start using it. If it is useless, nobody will care about it except you. Okay, now we will go for a break, but before the break, we didn't do enough quizzes. You have 5 minutes for the break, for the quiz, and 10 minutes for the break. And in 15 minutes from now, we will start the lecture. başında sadece.
Efendim?
Sadece başında kabul ediyorum. Sonra kabul
Hocam
etmiyorum.
dersi bölmemek için geldim.
Fark etmez.
Dersin başından
Fark
beri
etmez.
oturuyorum.
Başında getirmen lazım da kimseyi almıyorum artık dersin başı hariç.